we can go to the next speaker. We keep talking about experiments below the megahertz. So the next speaker is Ivette Fuentes. Ivette, you can start sharing your screen.
Thank you. Okay, yeah.
Yeah, so Ivette she, is from Southampton, and she will tell us about PC detectors. The stage is yours.
Thank you very much for the invitation. And like Francesco said, I'm going to talk about how can you use Bose Einstein condensates to detect gravitational waves. My background is from quantum optics, so this is the first time actually I think I meet with your community. I've been invited to some gravity conferences and high energy physics, but it's very exciting for me to be able to present this to this community. So I want to start by thanking all my postdocs and PhD students that along the years have contributed to these ideas and techniques. And also to my collaborators, both in theory and in experiment. At the moment, some years ago, Philippe Boyer, who's one of the strongest people in atom interferometry experiments, Chris Westbrook, who's done a lot of work on Bose Einstein condensates and phonons, and I applied for a synergy grant, and we almost got funding to get this experiment sort of started. And at the moment, we're doing a second try because we got asked for, we were I forgot the word. We almost got funded. We were recommended for funding, that's the word, and at the end it didn't work out, but hopefully this time. So this is just to say that this is a theoretical talk, but I've managed to engage the top experimentalist in my field on these ideas, and that we're actively working for funding. And also that all the things I'm going to present today have been, let's say, under conversation with both of them. So when one thinks about using cold atoms to measure gravitational effects, the first thing that comes to mind is atom interferometry. So in atom interferometry, you take, I don't know, say 10 to the 5 atoms, 10 to the 6, and you throw them into the interferometer because you're dealing with atoms. The mirrors and the beam splitters in this case are lasers. And what you do is that you take each atom in a superposition of 2 different trajectories and then recombine it. So this is about how do you actually use quantum superpositions and entanglement in order to detect gravitational effects. And I call this a single particle detector because in atom interferometry, the atoms don't interact. Actually, they are the interactions are avoided because if they do interact, they create unwanted noise in the system. And I also say that the detector is local because we have these 2 different trajectories and they recombine in a point in which you have the interference pattern. So when let's say if you wanted to measure the local gravitational field, the trajectories are different and there is a phase factor that the atom states picks up. And the precision in estimating, let's say, acceleration, in this case, the gravitational acceleration, goes like 1 over the square root of the number of atoms you used, the mode number k, and most importantly, the time of flight squared. So I call this interferometry in the spatial domain because each atom goes into a superposition of 2 distinct spatial trajectories. And it's limited, as you can see, by the time of flight. So the bigger the interferometer, the more precise it is. And this works very similar to LIGO, to electromagnetic interferometer, only that instead of having photons, you're having atoms. Now, I wrote here that it's compatible with Newtonian physics because usually when we describe an atom interferometer, we use non-relativistic quantum mechanics and the Schrödinger equation and the quantum mechanical inner products. If one wanted to describe this in a general relativistic fashion, then one has to be very careful. Perhaps one would have to use quantum field theory in curved spacetime. And so far, I haven't seen like a complete treatment on that. So one needs to just be careful with that. So because the precision depends on the time of flight, there's been amazing experiments trying to get the baseline longer and longer and longer. So for example, my colleague Philippe Boyer flew an airplane with an atom interferometer in free flight to get these time of flight's long, and he has an amazing experiment in France, which he has a tunnel, an atom interferometer in which each arm is 300 meters long. Here you can see the tunnel. And Ernst Russell, for example, has a tower in Germany. He was also part of the team initially, and they drop a atom interferometer in a tower for 20 meters or so. So the idea is always, in terms of applying atom interferometry for fundamental physics, is to make the times of flights longer and longer and longer. There are some applications, more maybe commercials. You would perhaps want to have a gravimeter on a chip, so you could have a portable gravimeter. And in this case, people take the same idea, but they interact with the atoms with fields, which slow down the atoms to get the longer times of flight, and try to miniaturize gravimeters. But we came up with a complete different idea on how you can use cold atoms to measure gravitational effects. So instead of having the atoms in free flight and in superposition in space, we are proposing to trap the atoms. Here you can see, for example, the atoms trapped in a square potential. So you can have typically 10 to the 5 atoms. For example, this is in rubidium, but if you do it with hydrogen, people have reached 10 to the 10 atoms. In sodium, 10 to the 8, 10 to the 9 atoms. So you trap the atoms and you cool them down. So a Bose Einstein condensate can reach 0.5 nanokelvin, but maybe some Kelvin or so on, microkelvin is normal, but 0.5 nanokelvin is a temperature that now can be reached in the laboratory. So when that happens, all the atoms occupy the ground state, well, almost all, and their individual wave functions overlap, and you have a big system behaving quantum mechanically. But actually the atoms interact and they collide, and this gives a rise to collective excitations. So these are called also phonons, or density fluctuations, and these are actually a relativistic quantum field. And we showed that if you prepare these in highly squeezed states, like highly quantum mechanical states, they become very, very sensitive to space-time perturbations. So now we're going to do interferometry, not in space, but in frequency domain. So that is like in the time domain. So now the system doesn't need to be big in order to have a good sensitivity. The trade-off is that the states that you're going to prepare, the quantum states, the squeeze states, have to live long. So that's a trade-off. But what you get in that case is that you can miniaturize detectors, and we have a patent on that at the moment. But it all actually started with an idea on how could you use this to detect gravitational waves. So now the interferometry is non-local, because at all times these collective excitations, these phonon modes, are sharp in frequency, but the atoms are completely delocalized in this volume all the time. So the interferometry is non-local. The states and the atoms interact with each other at all times. Because the atoms interact, this gives rise to a nonlinearity in the Hamiltonian, and this produces parametric amplification. So one of the things we're going to use to detect gravitational waves is quantum resonance and quantum parametric amplification, which makes things very sensitive. Now, we developed this whole proposal not with non-relativistic quantum mechanics, but it's actually all underpinned by quantum field theory and curved space-time, as you will see. So then it's compatible with both quantum mechanics and general relativity at these scales in which there's no back reaction and they're low energy scales. So the theory in this case seems to work well and is compatible, although this has not been demonstrated in the experiment yet. And that's also one of the very interesting points. So in principle, you would take some modes of your bosonic field. Depends on what you want to do. You have access to many modes. Then this would be the first step of your interferometer. This could be the analog of the bin splitter in atom interferometry, but here you can do much more. You can mix many modes, or you can even squeeze them and have, like we call it in quantum optics, active interferometry. You can do 2-mode squeezing and so on. Then you have your interaction with your system. So this could be your gravitational wave. And you have the inverse transformation to sort of close the loop, but in frequency space, and then your measurement. So as I was saying, this allows you to miniaturize detectors. There's already work in progress trying to put Bose Einstein condensates on a chip. And it still has very high sensitivity, even perhaps in theory more than the other proposals, and high resonance to noise. Now, we don't compete with atom interferometry for gravitational waves because the frequencies are very different. And I'll say a little bit about that. Now, just listening to the question that Valerie made about others. Was it Valerie that asked about other systems? No, you asked about the tensor structure. I'll go to that. But somebody asked about other systems and other frequencies. So I'm going to talk about today, how would you implement this in a Bose Einstein condensate? But actually you can implement this in another system. For example, I was recently, 2 weeks ago, invited to give this talk to the group in Chalmers, where parallel dancing has superconducting circuits. So in the case of superconducting cavities and circuits, the frequencies are different, but you have the same ingredients. You have phonons in the quantum regime and so on. So we're looking into how could you implement the same ideas in a different system to achieve different frequency ranges. So we've done a lot of work in the last years. This started in 2014. And well, today I'm going to tell you about how could you use these ideas for detecting continuous source gravitational waves. But we have a paper on constraining dark energy, measuring proper accelerations. Like I said, we have a patent on measuring the gravitational field and its gradient. And I also want to make some comments on how could we perhaps use this for searches of dark matter. But if we're able to show that changes in the space-time produce changes in the relativistic quantum field of this BEC, then this would be some demonstration of some of the key principles of quantum field theory in curved space-time as well. So a Bose Einstein condensate, as I said, consists of 10 to the, let's say now 10 to the 8 atoms cooled down to the ground state. If the atoms did not interact, then you could describe the whole system in the ground state with a mean field, which obeys a Gross-Pitayevsky equation. However, the atoms collide, and then before you have to look at a perturbation to the mean field, which are your phonons. And in the case of a uniform density, this takes a very simple form. So what I'm going to show you is applies only to a Bose Einstein condensate in a box potential where the density is quasi-uniform. But typically Bose Einstein condensates are trapped in a quadratic trap. And in principle, you could do the same, only that the equations would be more complicated, and we haven't done that. But in principle, there's no fundamental reason why you couldn't do that. So this is the Lagrangian of the atoms in the Bose Einstein condensate. You have here your kinetic energy. You see here the underlying space-time metric and the determinant of the metric. You have a relativistic correction to the potential. So this is the trapping potential of the BEC, and these are the collisions in terms of the BEC. So using this Bogoliubov ansatz, where you have the perturbation to the mean field due to the collisions of the BEC, if you plug this into the equations of motion, then you get for the phonon field a Klein-Gordon equation in an effective curve metric. So this is how the effective curve metric looks like. You have the density of the Bose Einstein condensate, the effective speed of sound, the speed of light. This is the underlying space-time metric, and these are the velocity flows in the BEC. So what analog gravity is, you probably heard about experiments, for example, by Jeff Steinhauer in Israel, that he plays with the flows of the BEC and simulates a black hole and then makes like an analog measurement of Hawking radiation, for example. So that's basically playing with the density or the speed of sound or the velocity flows to make this behave like a space-time. But usually the real underlying space-time is neglected and ignored and considered flat. So we did the opposite. We assumed that the flows are, the spatial part of the flows are zero. And then we look at how changes in the underlying space-time metric could produce observable changes in these states of the phonons. So this metric was done by several groups before in the flat case and in the quantum case, and my group combined this to look at the quantum fields and curved spacetime. So as you see, the underpinning theory of this whole thing is quantum field theory and curved spacetime, not just non-relativistic quantum mechanics. And as far as I know, this is the first sort of proposal in this sense of like quantum technologies that is underpinned by quantum field theory and curved spacetime. So we have the Klein-Gordon equation in an effective metric, and when we have a time-like killing vector field, that in this case is just dt, we can find the solutions to the Klein-Gordon equation and quantize our field, associating creation and annihilation operators to our solutions to the Klein-Gordon equation. And in the case of the flat space, we see that the effective metric ends up looking very similar, just like the flat metric, only that the speed of sound is replacing the speed of light, and you have this conformal factor. Now, because the phonons are a massless field, this conformal factor always cancels out. So it basically just amounts to us having the same sort of field quantization, only that the speed of sound replaces the speed of light. The frequencies of the phonons are given in terms of the speed of sound in the BC and the size of your box. So I'm going to show you 1+1 dimensions, but we've now done work in 3+1 dimensions. So the Klein-Gordon equation in this case is very simple. It's just a wave equation, and the solutions are exponentials, but we're putting the BC in a box potential. So we put boundary conditions, and this gives the modes that are terms of these sine functions. So now you want to look at what happens with a system if you have a gravitational wave. So the metric is given by the flat metric plus the usual perturbation. That's the quadrupolar. Usually to my community, I have to explain this a little bit more, but for you guys, it's very obvious. So now the metric that the phonons see is very similar to the usual metric, but here again, you can see the speed of sound replacing the speed of light, and the conformal factor that again is going to be just, you know, irrelevant in this case. Now, because we're in a one-dimensional trap, we're just looking at perturbations in one direction. And this is where the question by Valerie comes in, that she was asking, can you see this tensor structure of the gravitational wave in this case? And in this case, the answer is yes. I'm now showing you the results for one-dimensional BC, but we are now, and some of it is already published, looking at a three-dimensional box, and also spheres and ellipsoids. And in that case, you can capture the quadrupolar characteristic and the whole tensor structure, at least in some of the directions for the gravitational wave. But in one-dimensional case, it looks very similar, but very simple. You basically just have this sinusoidal perturbation. So here you can see we're looking at continuous sources, which are monochromatic. This is the amplitude of the gravitational wave, and this is the frequency. And what we're going to do is we're going to pick two modes of the phonons such that the sum of the frequency is in resonance with the gravitational wave. So in order to describe what happens to states of the phonon field when the gravitational wave comes by, we use Bogoliubov transformations to calculate that. And basically the proposal now is a three-mode application of the frequency interferometry scheme that I showed you. So we take all the atoms in the ground state are this red mode here, the ground mode, which we call the pump, the bulb. They have different names, and you prepare that in a coherent state, and this is the state that's going to have most of the atoms. Then you change the size of the trap experimentally in a periodic way, and you can then choose what two frequency modes you want to excite. So you excite, let's say, for example, this green one and this blue one. By changing the state, what you prepare is a two-mode squeeze state of those modes. Then what you do is that you mix the bulk, the ground state, the pump, with these two modes with an operation that you can see here mathematically in the covariance matrix formalism. It's called a tritter. So basically it's a three-way beam splitter. So all the modes are mode mixed between them. Then this is the Bogoliubov transformation given by the gravitational wave. And then we do the inverse transformation to close sort of the loop in frequency space. Oops. So we came up with this idea in 2014, but in 2014, we were only considering the two modes and two modes squeezing them, and immediately they're measuring. And what that was requiring was high phonon numbers, so high squeezing, which some people wrote a few papers criticizing that it was not possible to get those degrees of squeezing. And also, we were not really, at that time, people knew very little about how long can phonons live at different frequencies. So we made a guess, educated guess based on some papers, but the criticism was really focusing that it was not possible with today's technology to get these long phonon times. Ooh, 5 minutes, okay. So we've now showed that if you add this, you get much better sensitivities. So we use quantum metrology. Maybe in the questions we can talk about the quantum metrology techniques of how you estimate the precision. But the precision is bounded by the number of measurements and the quantum Fisher information. So we calculated this figure of merit for the precision many years ago in terms of Bogoliubov coefficients. So you plug in the Bogoliubov coefficients there for your gravitational wave, and we get this sensitivity. So it's complicated, but you can write a nice and clean equation on it. It depends on the atomic mass, on the angle of the mixing, on the number of atoms in the ground state, on the number of atoms that you were able to squeeze, on the parameters of length and area, on the scattering length of the atoms, on the integration time that we are considering like a year, on the lifetime of the phonons, and on the frequencies. And all of these parameters are sort of connected to each other, so you have to be careful. So one of my postdocs here made a numerical analysis, like an optimization, taking all these parameters into account and all the constraints. And these are for the different, the sensitivities that we got for the characteristic amplitude in terms of frequencies. So this looked very promising. We got obviously very excited about it. These are the constraints. So because you're working with a Bose Einstein condensate and you're looking at phonons, you need to make sure that you're in the phonon regime, that you're in the weak interaction regime, that you're in the ultra cold regime. So these parameters, as you can see, there are quite a few of them, and there are all have to obey important constraints. Now, Mike was also put these two things on his slide. I was very interested in that, saying like, what are the sort of things you would expect that you can do with your proposal? And the second thing that he mentioned is like, well, I mean, you should be able to test that actually this can be very complicated so that it works. So we have a paper showing that how you could test it. So if you have a BC here and you put a little a bead like the one that we just heard about by George. So if you oscillate a bead close to the BEC and create space-time distortions, then you should be able to test that indeed the states of the phonons change in the way that we predict. So you could in principle do some tabletop, more simple experiments to test that actually this works. And well, we've done many studies with noise and decoherence and so on, which is in these papers and also on a recent thesis from one of my students in Vienna. And here are some of the numbers that we get. So, well, we're at the moment exploring different species, but you can do this with sodium, with lithium, with rubidium, with all of them are different. And with all of them, we get different numbers. This is just one example, but we're taking also very conservative numbers. So for example, these are the current lifetime of the phonons that people are sort of happy with. But what you would have to do to get much higher sensitivities here would be basically get longer phonon times. So here you can see a plot where you can see how the sensitivity improves when you have higher phonon times. So if you were able to have this even push it even further, we really could get very high sensitivities. Well, I compare these to some models for glitches of neutron stars. And it again looked promising, and I also put it into the plot, but this is a bit unfair because I'm just looking at the characteristic amplitude, and this is obviously theoretical, while the others are experimental, but I just wanted to get some sort of sense of where we are. And I was also looking at what are the energy scales for surges of dark matter, for ultra light dark matter. This is what CERN has been looking for, but we would be able to be looking at lower energies in these scales here. I heard from John March Russell that dark matter would create periodic perturbations of space-time, which are long-lived and monochromatic. So I think this is exactly what we had put in our model. And well, I just wanted to come to the end by saying that we're not using interferometry in space, we're using interferometry in frequency. So delta L over L in this case doesn't play any role. We're basically using resonance. So this is very similar to a Weber bar. But here you have, well, I found this that Weber bars were cooled down at 4K, but now reading more, I learned that they can be cooled down to the millikelvin scales. But a nano BEC, you can cool down like 10 orders of magnitude beyond that to half a nanokelvin. And the thing is, even if you were in the millikelvin scales, your modes of vibration are still classical. And even in our case, if you use thermal states, you would not be able to detect anything even with a BEC. So basically what a BEC is a quantum Weber bar in which you're using the modes of vibration of the BEC to detect a gravitational wave, but you're squeezing them. And that implies sort of entangling the atoms and so on. And you're using parametric amplification to detect. So here is also comparing the speed of sound divided by the length. And you can see typically in rubidium, the speed of sound in a BEC is 10 millimeters per second. So if you want to resonate between 10 to the 5 and 10 to the 3 and 10 to the 5 hertz, you would need a system of 10 to the minus 1 and 10 to the minus 3 millimeters. If you do this with the speed of light, then you find 3 to 3,000 kilometers, how your box should be big. So as I said, we've also looked at different geometries. And we have the same idea we use, but to detect the local gravitational field. And we're having this patent going now to the international phase. And I'm going to stop here to get some questions, and just to say that, well, this is really bringing together quantum effects and GR. So we hope that the development of this also leads to put some pieces of the puzzle together in our understanding of quantum mechanics and general relativity. So yeah, sorry, I had to run, but with 25 minutes, it's kind of hard to go through the whole thing.
Yeah. Thanks a lot, Ivette, for this nice presentation. We already have a question by Diego.
Hi, can you hear me? No?
Yes.
Hi, thank you. Well, it's also a question for, in general, when people are computing these sensitivity curves, so the gravitational wave you showed is in the TT gauge, but to make the calculations in your detector, you need to change to the detector frame. So is this something that you care about in your paper? Like,
yes,
I mean,
we have a paper on that. Actually, I can show you the reference, but we did the calculation in both frames, in the detector frame and in the TT frame. They're done in both, and you can compare them. So that is a paper with Richard Howell and Dennis Ratzel. So yes, because we have, I can send you the reference, but we did it in both frames just to make sure that we had the right thing.
Thank you.
Mike?
Yeah, so very nice talk. When you use laser cooling to cool your BEC, I guess, and to get to the low temperatures, and it's parametric. Do you know how that affects the lifetime of the phonon modes? And what are the effective Q factors you know, because as a resonant bar person, you usually think of the Q factor of the modes.
Yes, so the Q factor is going to be given again by the lifetime of the phonons. So the lifetime of the phonons depends on many things, but we have here like my student wrote a thesis, and it's now online, where we study really in full detail what are the lifetime of the phonons for different species and for different parameters and conditions, because it's very dependent on the species that you use and on the experiment. But it basically depends very highly on something called three-body recombination. So you have many effects. You have the thermal, you know, heating and trap instabilities, two-body recombination, three-body recombination, but a big killer is three-body recombination. You can have three atoms that collide, form a molecule, and you lose it. And that is going to sort of limit how long your phonons live. And then the Q is basically 1 over the lifetime of the phonons.
So do you know what that is, more or less, ballpark?
Yes, I have it. Like the lifetime of the phonons is, for example, given
just as Q factor, my brain works in Q factors.
So so I don't have it in terms of Q factors, no, but it's easy to convert them, because the Q factor is essentially 1 over the time. But yeah, I can write it down. And this is when you get two different communities talking to each other. No, we usually think about what is the lifetime of the phonon, but it's easy to translate into the Q factors. But I don't have these translated at the moment.
Okay, thank you.
Thanks.
George.
Hi, thanks for the talk, Ivette. Very interesting. I was quite interested in your idea of using a bead to calibrate the BEC detector. And I guess I was curious about, I mean, the mass of the bead's pretty small, so I was curious about what the distances you have to achieve to make a significant gravitational perturbation with it would be.
Yes.
Is it microns or?
Yeah, so the BEC is 200 micrometers. And the bead, we have a paper on that. So I'm trying to remember the numbers of that, no? So the bead, I guess, is maybe a similar size, maybe half the size, so like 100, I don't remember the size of the bead, but the distance between them is, it's a bit bigger than the radius of each one, but isn't within the scales. So you have to bring them fairly close. But you know what? I'm feeling a bit bad of like sort of trying to remember the details and guessing. I can send, like we have a published paper on that. But I think that it has to be close but bigger than the radius. So it could be like 10 times bigger, but I'm not remembering very well. Yes.
Okay, thank you for answering.
Yeah.
Now, Tatiana, it's your turn.
Yes, okay. Thank you for the very interesting talk. I would like to ask you about the number of parameters. You presented now on this slide 12 parameters. It's very much, too many. But the question is the following. It's very interesting idea to use such BAC detector, but what is the main parameter which is necessary for the improvements of gravitational wave detection, maybe so.
The tricky one is the lifetime of the phonons. You see, in atom interferometry, what you need to get high precisions is the time of flight. So you need to make them big. In this case, it's interferometry in frequency, basically in time. So you need to make them long-lived instead of big. So these are the lifetime of the phonons, and this is where we have to improve. So this is where I put the times of the real experiments. Now, these times here are experiments that, you know, numbers that experimentalists would say, okay, I can do this in my lab right now. But where the challenge would be, because look, here we get some sensitivities that look 10 to the minus 21 and so, but if we wanted to go beyond that, we would have to improve basically on this, which basically means getting a hand on these sort of effects that I was measuring, like 3-body recombination and so on, and 2-body losses. The atoms collide, they form, and they bond, they form other molecules, you lose it, and then you lose the state, and you need the state to live long. So that is where one of the challenges are. I would like to also say something about, because Mike mentioned on what could you do also in order to distinguish local noise from really like the signal. And these are very cheap systems. In principle, every university in the US or in the UK could afford one. I mean, you know, not every university in the world, but they are cheap systems to build. So if you had many BCs, and some in America, some here, some in other countries, in Japan or so on, you could use the correlations with the time signals and get rid of local noise. I mean, it's similar to what LIGO does, but in that case, you have just 2, 4, 6 detectors, but here you could have hundreds or more of detectors. And I think this would be one of the ways in which you could get rid of noise. And yes, like I said, you can do it 3-dimensional, but you can also have many detectors distributed on the Earth, orientated in different ways, or with different geometries. And hopefully that would give you more information about the tensor structure of the gravitational wave.
Okay, thank you.
Okay, so we have another question, but we are running very late. So Fernando, if you don't mind, we can postpone it to the discussion session later.
Yes, okay, don't worry, we can postpone it. No problem.
Yeah, okay. So thanks again, Ivette, for this very nice talk. And I stop here.
Thank you very much.